Hi, I'm Rohit. I am leading an ML engineering team at Nauto. We at Nauto affect driver behavior and reduce high-risk events mobility ecosystem through a solution that spans all the way from hardware to cloud. And in my talk, I'm going to be talking about how we use Scylla to power some of the infrastructural pieces that we use at Nauto. Specifically building trips, matching drivers to trips, and doing this in a consistent manner on top of Scylla's eventual consistency model. I hope you enjoy the video. So at Nauto, we have this device that helps find all the distracted sea monsters out there. Well, helps find all the people who are distracted and prevent distracted driving and to make roads safer. Now, in order to do this, we have a device that we've installed in the car, and we have this full solution in the cloud. And we have analyzed almost 400 million miles of video. And using this, our ML models can save tons of collisions and have saved a lot of money for the commercial fleets. In order to do this, we need two pieces of infrastructure. One is understand what really is the trip, and the second is match the driver to the trip. Now, let's think a little bit more about the first one, which is identifying a trip. This is effectively constructing a time series and merging a time series problem. So what do we have? The device collects what are called vehicle state messages. These are some samples of data with a timestamp. It sends it to the cloud. In the cloud, we send it to over to Kafka on a topic which is sharded by the device ID. These messages are then consumed by many workers, and the sharding by the device ID helps such that all the messages from a particular device only go to a single worker. This invariant helps with a few things, so you don't need like global locks on whatever you're processing related to a particular device. Mostly, there are still some cases where you would have some issues. What do we do at each one of these workers? At the core, it looks at the neighboring trip segments, or if you will, the time series segments around the particular time point, merges them together, and saves it back to the database. And for the database, we use Scylla. So let's look a little bit more into what the merging step is. So take two trips. One is at 8 a.m., the other is at 8:40 a.m. And let's say a new small trip segment came in, which is around 8:15 a.m. So if I want to now look up the neighboring segments, I'll pick up these 8 a.m. and 8:40 a.m. trips, merge all of this thing together, construct a big trip from 8 a.m. to 8:55 a.m. Once I have done this, I'll save it down to the disk. I'll delete my existing old trips. And at the end of it, I just have a single trip in Scylla. Now, at this point, you should ask the question, wait a minute. There was this step in between where you where you saved a trip, and then you deleted a couple of trips that were components of it. What happens in between if, let's say, a process died or whatever happens? You'll have some duplicate data in the disk. Now, you could say, yes, we could do this using lightweight transactions. You could do it using batch log, but all of that adds some cost. And that's not the only source of problem. One time, and I'm pretty sure this has happened more than once, we had noticed problems where Kafka was not delivering as all the messages from that one device to one worker. It was basically flipping partitions quite rapidly, and many workers were getting messages from the same device. This tends to happen sometimes. There are other problems that can happen. There can be bugs in the code, and eventually we all have a friend known as Murphy who can create all kinds of problems. So this begs the question of what is consistency? How do we keep consistency in our data? And what does really consistency mean? Now, if you look at all of these operations, actually, first show of hands, how many over here have come from a SQL world? Have used SQL? Yes. So I don't know, but when people typically come from SQL world, the first thing when you start using NoSQL is like, wait a minute, what happened to my consistency model? I don't have any guarantees on my data. Do I need to then use full consistency for every operation that I'm doing? But then that defeats the purpose, more or less going to a NoSQL system. So the answer to that question is, what kind of consistency do you need? Do you need consistency on your data layer, or do you need consistency in your application layer? Do those duplicate trip segments actually matter to you or not, effectively? So let's look at this a little bit in more detail, and in order to do this, I will rewrite that one particular step, the trip merging step, as a function. Think of it, it takes two trip segments, merges them together, and produces an output. And let's look at a few properties of this particular function. First, let's say I have 3 trips, 8 a.m., 8:15, 8:40 a.m. Does it matter if I merge 8:15 and 8:40 first, or does it matter versus 8 or 8:15 first, and then with the third one? It doesn't. Eventually, you should get the same trip with the same time series. So F is associative. Second, does it matter in which order I give trips to this trip merging function? Like 8 a.m. and then the 8:15 a.m., or 8:15 a.m. and then the 8 a.m.? I mean, effectively, your output is again the same. So the trip merging function is commutative. Then the third one, which is, let's say I have 8 a.m. and 8:15 a.m. I am merging this trip. And then, for some reason, I got a duplicate again. Maybe I got extra messages. There were some data inconsistency issues under the underlying layer, whatever is the reason. So I got the 8 a.m. trip a second time. What happens when I merge all of these things? I should still have the same trip, 8 a.m. to 8:35 a.m. And so in this case, F is idempotent. Finally, it doesn't matter how many times you run this function on the same set of inputs, your output is going to be the same. If I merge trips again and again, I'll get the same merge trip. So F is very deterministic. Given all of these, there is work in the literature that shows if your algorithm follows these properties, then you can have a system that produces application layer consistent output, whatever that means for your particular application. In this case, it's just having a consistent view of the trip. And you are guaranteed that you can have this execution. You can have a distributed coordination-free execution program. So let's look at a couple of examples here of how that would be, and to give an intuitive sense instead of diving into all of the theory for this. So let's say worker 1 loads trip 1 and trip 2, the 8 a.m. and 8:15 a.m. trip, merges them together, constructs this 8 to 8:35 a.m. trip, saves it back to the database, and then deletes the 8 to 8 a.m. and 8:15 a.m. trip. Worker 2 now sees these 2 trips, loads them, constructs a full merge trip, saves it down to the database, and then deletes the first 2 trips. And this is fine, nothing special over here. Now let's look at a second case where there is a little bit of a race going on between 2 different workers. Worker 1 sees trip 1 and trip 2, loads them. Before it can do anything with them, worker 2 sees trip 2 and trip 3, loads them. Now worker 1 generates a merge of trip 1 and trip 2, saves that down to the database. Worker 2 merges trip 2 and trip 3, generates a merged version of that, saves it down to the database. Now, if you see in the database, currently you have a bunch of stuff, a lot of duplicate stuff. This, in some cases, you would say is a lot of inconsistency. However, if I apply the same function f for any reader that is reading data from the database, it will clean this data up and present it in a manner that is consistent. So let's say after this worker 1 continues to run, it deletes those input trip 1 and trip 2. Worker 2 now deletes trip 2 and trip 3. Trip 2 is already deleted. There's nothing to do. Trip 3 gets deleted. Now, worker 1 again looks at this. It loads these 2 trips. There's an overlap, but that's fine because this merge function is idempotent. And it generates a merged version of this trip, saves it down to the database, and then deletes the former 2 tables. So at any point, if you look in this whole sequence, if I had read, if some other system came in between and read all the data and it applied that same function, the merge function, it will always have a consistent view of the data. And there's never any consistency, there's never any data loss, there's never any duplication from the application point of view. So basically, we get application level consistency by carefully formulating our problem without having to depend on any full consistency from your underlying system. And using this helps keep a lot of people happy who are coming from some other places, and they see all these things that, hey, what is all this? I'm getting some inconsistent data. And so, and yes, and we can do this on top of Scylla without having to use full consistency. The second thing that I talked about was matching a driver to a trip. Now, this problem happens to be very similar to finding similar images. Let's look at what we do. The Nauto device collects snapshots of a driver, sends that up to the cloud. In the cloud, we take these snapshots, we compute a representation of that by passing it through a few neural networks. And I can talk more about the neural networks later. But basically, we have a 128-dimensional vector that is a representation of each one of these snapshots that is computed. And this is then used to find who the driver is. This is also somewhat privacy protecting because it is not using a model that is already out there. Since it's a model that is made by us, you cannot just use the vectors and look up into any pre-existing database to find to identify a driver. So what does the next step involve in order to match this driver to a trip? You have this representation of the driver coming from one image. You have many images that are saved in the database. So let's say you have 3 images for driver A, 3 for driver B, many more for many of the other drivers. I want to load up all the representations for all of these drivers, and then I want to find the one that is closest. So that effectively is my problem, and that is the same problem as finding any similar image in general. Let's assume we have 10,000 drivers, and each driver has something like 10 images associated with them. It means that now you have 100,000 images, 100,000 128-dimensional vectors, which is a lot of data that you need to load up at every single time when you are matching a driver, and very quickly your problem becomes untenable. So what do? We have a schema where we save, and we break these sets of images down into groups. A group can be thought of as a logical grouping. It could be that, in our case, we don't need to match across different fleets, so a fleet is a good grouping. You don't need to match across different georegions, so a georegion could be a good grouping. You could have a more principled approach, which is called locality-sensitive hashing, which converts that vector into a hash. And if you take, and this hash is basically something where most of the similar images will actually hash to the same bucket, so they will collide as opposed to preventing collisions. And things that are dissimilar will often be separate. It could be that a few images that are dissimilar get into the same bucket, but that's OK. You can filter it out at a second step. So our partition key is the group. Then you have the clustering key of the driver ID and the particular exemplar or the representative image ID for this particular driver. And there could be many of them. And finally, the vector itself plus some metadata, we actually save it in a serialized protocol buffer, and that is called details over here, and put it down. We initially used JSON for human readability and debugging, but that quickly was making the data size very big, and it would slow things down. So we switched to using Marshall protocol buffers and saving that. So let's see the next step. So now that I have found my drivers who are, let's say I'm able to load all the snapshots and I'm able to find all the drivers who are close enough to this particular snapshot, I get some probability numbers. Let's say I have 3 images over the course of this timeline, and I load these 3 images. I have probability numbers. Say snapshot 1 matches driver A probability 0.3 with driver B probability 0.4, and so on. I combine these together by using a probabilistic model. It's similar to Bayesian inference. It's called Dempster-Schaeffer evidence theory, if anyone wants to look it up. And then I present a final verdict saying that this driver matches, the snapshots that I received from this strip matches actually this driver, so effectively this strip is matching this particular driver A. And note, this is independent on the number of observations. Each time the trip is extended, each time I'm getting more snapshots, I can go back to Scylla, load up all of my snapshots from a timeline, and I can, again, redo this analysis to see who is the best match. After some point, you can heuristically say, I've already done the match and it's good enough. By doing all this, we get a pretty high precision. So our precision numbers are of the order of 99.9%. Recall, where we are matching with an existing driver really well, is almost 97.1%, with only a little bit that we are not able to match. So that's the main part of my talk. And I would like to thank everybody for coming here and listening. Thank some of my team members who are also present in the audience. And yeah, any questions that you have, I'll be glad to answer them. All right. Thank you.
Any questions? Yeah. Just a second. It's being recorded, so we want you to speak to the microphone.
Hi. So in your example of merging the trips, you said worker 1 and worker 2 produce results independently, and at the end of the example, worker 1 merged the 2 intermediate segments. What guarantees that worker 1 actually gets back to rescanning the database?
Sorry, what is the guarantee that worker 1 gets back to?
Yeah, what's the guarantee? So you said worker 1 merges ranges 1 and 2, worker 2 concurrently merges ranges 2 and 3.
Right.
What guarantees that either of these workers goes back and spots the 2 intermediate results? I thought you said they were driven by Kafka, so there would only be 3 events in Kafka?
Oh, so let me understand what is happening. So there is a small step I missed in between. It's saying that, let's say you are getting there is some new message that is coming from a device, or there's some other event that is causing one of the workers to read the data. The third time when it is reading, it need not be worker 1. It could be worker 3 altogether. It could be a completely separate worker. But still the same set of, the same way the whole program executed would apply. It just depends on what, at that point, the worker read. Does that answer the question somewhat? Okay. All right.
Any other questions? I saw some more hands. Any other questions? Yeah. Just a second, Shlomi, sorry. I'm doing my exercise.
So you said that you have a lot of images and
Yes.
you try to match them, but you have also the idea of the device. So logically, on the same device, you'll see similar images. Is that taken into account?
So that's a good question. I don't particularly talk about this over here, but if you look at this particular place where I am taking all of these, the results of matching to a particular snapshot into account, there are lots of other observations that can be taken. And they are taken in the form of some of them are statistical observations. This driver is typically driving this device A, or this driver is typically shuttling between device A and B. And those are some additional signals that are taken into account over here, and they're combined along with these phase signals using the same framework to generate an inference. So yeah, those signals help also, in addition to the phase signals. Thanks.
And you return just one row at the end. So to build